Okay, questions about the first part of, I guess, Alkene addition, anything left over from E1, E2. We should probably start having a quiz before class so that people come. I'm not kidding. So what questions do you have? Okay, then let's start with that one. What would be the major product of this reaction? Come up and grab a little mini whiteboard, a washcloth, and preferably a black dry erase marker, although I suppose if it's a dark color you could use that if you feel the need to use a Okay, so what's the major product of this reaction? I should add one thing to this without rearrangement, although I don't know that that's necessary. So what would be the major product of this reaction? And then when you have your answer, you can go ahead and hold up your whiteboard and I will just nod that I see it. And if you're in the back, you want to write big or move up. That's probably not big enough. So when you write your final answer, write it like almost full board. And when you have your answer, you can go ahead and hold it up so I can see it. Okay. That's your final answer? Okay. 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 Interesting. Okay, I give you another 30 seconds or so to write your answer if you have one. Is that a double bond? Is it a double bond? Okay. Although we could. Okay. Okay, what do we have? I just want to see how everybody did. Okay, huge ring, but your letters have to be equally proportionally big because I can see the ring. Okay. Tommy, okay, I can see that. Okay. Because I can see the ring, I just need to see any groups that you have attached to it. Okay, so in chapter 12 that we're on, we're now going to react double bonds. We know how to make double bonds, and we'll go back and we'll look at those E1s and E2 reactions to make them. But now what we need to do is now we need to be able to react the double bonds. So we're going to have probably a dozen reactions that we're going to learn in the next 2.5 weeks or 3 weeks. Before the next test, there's going to be a lot of reactions. And for each one, ultimately we need to know, what am I adding to the double bond? in terms of my net result. So that's going to be question number 1, is what am I adding? And question number 2 is going to be, how am I adding it? So let's talk about this. What am I adding to the double bond? If I'm writing the mechanism of this, what am I going to add to the double bond here? The double bond is going to react with what? H plus or H2O? H plus? Why? Okay, so what is the double bond? Electrophile or nucleophile? Is it electron poor or electron rich? The double bond. What do we think? It's a nucleophile, it's electron rich. What's the source of its electron richness? The pi bond. So the pi bond is what's going to make it electron rich. So electron rich things have to react with electron poor. So what is water? Electrophile or nucleophile? Water's been a nucleophile all along because it's got lone pairs. So the double bond must react with the H plus. So that means I'm going to take that double bond, that pair of electrons from the double bond, and I'm going to use it to bond the hydrogen. And I have two choices here. I can bond it to carbon A or I can bond it to carbon B. So let's say I do that. Let's say I bond the hydrogen to carbon A to begin with. And let's say I bond the hydrogen to carbon B. Now when I bond the hydrogen, the H plus, to carbon A or B, what happens to the other carbon in the double bond? We're not being very responsive. Maria.
When it becomes the carbocation?
It's going to become the carbocation. So if you think of it this way, the A and B are sharing each one electron each to form the double bond. But I'm going to take the double bond away, and I'm going to use it to bond the hydrogen to either A or B. The other carbon then is going to lose its electron. So if I bond the hydrogen to carbon A, I'm going to end up with carbon B having a positive charge. If I bond the hydrogen to carbon B, carbon A is going to have the positive charge. And so that's my choice. My choice is always to add the electrophile, in this case H plus, today it's H plus, to either A or B. And so if I add it to A, and if I add it to B, I get two different carbocations. So which carbocation is going to be the most stable? The one corresponding to A or the one corresponding to B? Let's say it all at once. On 3, I won't say the 3. Okay, A or B? 1, 2, B. Thank you, B. Why B? Because it's a tertiary carbocation. So my choice is forming a secondary carbocation or tertiary. Which one am I going to form? I'm going to form the more stable one. So that means that I'm going to form more tertiary than secondary. Okay. Now, at this point, this is the only new step of this mechanism. Because now what I'm going to do is now I'm going to react that carbocation with water. I can react each one of those carbocations with water. And what do I now have? What mechanism? What mechanism did we add a neutral nucleophile to a carbocation? SN1. So at this point, it's nothing more than an SN1 reaction. So for B, my water is going to come in, and I'm leaving transition states out here, but you will be asked to write the transition state. But I will then add the water. That will give me the oxonium ion. And then what happens next? What happens next?
Hydrogen donates electrons to oxygen.
I'm going to lose the proton, right? I'm going to lose H plus to form the final product, which most people had eventually. Okay. So this would be the mechanism without the transition states for adding H plus H2O to a double bond. So whenever what I'm going to be doing, or what we're going to be doing for the next couple weeks, is adding stuff to double bonds. We will always add one group to one side, the other group to the other side. So you're going to want to come up with a list of reagents, and I think there'll be eventually a table there'll be a table of different reagents and what they add. But the ones for today that were in the reading were adding H plus H2O, adding HX to the double bond. And so when we add H plus H2O to the double bond, what am I adding? H and OH. When I add HX, meaning HCl, HBr, what am I adding? H and whatever the halogen is. Okay. So in this case, the H added to the bottom carbon and the OH added to the top carbon to give me the major product. Okay. Okay, everybody with me so far? So then there was a rule that was developed for this, that before people knew what the mechanisms were, they could predict what the product was by doing a bunch of reactions. And that's what's called Markovnikov's rule. Although there's now controversy because the paper that Markovnikov wrote didn't really have anything to do with this, but yet somehow he was given credit for it. And there are people that say, well, since he never really proposed this, should we be giving him credit? And so there's that controversy. It's not like the Zaitsev rule, where Zaitsev, I think, really did determine that, although I haven't looked at the paper. This is like a Russian and it was a German paper. But there's anyway a controversy as to whether or not he should be given credit. But we still call it the Markovnikov rule. And the Markovnikov rule says that you're going to add the H to the carbon in the double bond that has the most hydrogens. And then the other group adds to the other carbon. So that pattern was known. And Markovnikov's rule, I believe, it's only been in the early 1900s that it was actually ascribed to him. Because that in the late I have organic books from the late 1800s, and they have nothing about Markovnikov's rule in them. So it's only been 120 years that we've known about this. So you add the hydrogen to the carbon in the double bond that has the most hydrogens, and that's where the other group goes. When that pattern happens, we call that Markovnikov addition. Okay. There will later on be anti-Markovnikov addition, and that's where the hydrogen goes on the carbon that has the least number of hydrogens in the double bond. Markovnikov knew nothing about this. The people that gave the name to that knew nothing about the mechanism, but we now know why, because you have to add the hydrogen to the carbon with the most hydrogens, because that's going to form the most stable carbocation. Because where you add the hydrogen, the other carbon gets the positive charge. You want that positive charge on the carbon that's most substituted. And the most substituted carbon, by definition, cannot have the most hydrogens. So when you add your H plus from HCl or from H plus H2O, you're always going to end up with the Markovnikov product. Okay. Right. So there's basically three things we have to know about every reaction. So let me change this mechanism, and let me put two methyl groups here. Okay. Now, what we already know about H plus H2O and HCl or HBr, my first question is, what are they adding to the double bond? H plus H2O is adding an H and an OH, and HCl would be adding an H and a Cl. So my first question, and the first thing you need to remember for each set of reagents is, what am I adding to the double bond? My second thing that I need to know is, how am I adding it? Markovnikov or anti-Markovnikov? And so in this case, how am I adding? I'm adding by Markovnikov's rule. So question number one, what am I adding? Second question, how am I adding it? Third question, how am I adding it? What's the second, how am I adding it? If I said I was going to add HCl to that molecule, how is the HCl going to be added? And your choices are going to be A, 100% cis, B, 100% trans, C, 50-50, or D, some random percentage. So if I add the HCl to that double bond, how are the H and the Cl going to add? I'll give you a couple minutes here. Discuss with somebody close by. Since we have our boards out, we can just write the letter big on the board. I find the boards to be as engaging as the cards. Does it mean that you're going to be identified with your answer? Yes, but am I going to remember? No. Okay, so discuss for a minute, and then choose either A, B, C, or D. And be prepared for an answer, prepared for me to ask you why you chose your answer. Okay, okay, okay. Okay, guess we don't write letters down. You're fine. Okay. If I've seen it, then you can just go ahead and put your... Is that the answer for the group? Yeah. Anybody else not giving me an answer? Did I get answers from everybody? Kate, did I get answers from you yet? Okay. Okay, so it seems as if I got the same answer from everybody. C. Why? Why is the H going to add 50-50? So I'm going to end up forming a carbocation. So if I added, for instance, the H, let's just say for the sake of argument, I added the H from above the plane of the ring to the top carbon. What's going to happen at the bottom carbon? I'm going to end up with a carbocation. How's the chloride going to add to that carbocation? You all told me it's going to add 50-50. Right? 50% of the time it's going to add from the top, 50% of the time it's going to add from the bottom. Why is that? Because I'm adding the chloride to a carbocation. It doesn't matter if it's primary, secondary, or tertiary, because remember the carbocations always have the lobe above and below the plane, and so that's how the chlorine is going to add. It's going to add 50% of the time above to the lobe above, 50% of the time to the lobe below, and so I'm going to end up with adding then the chloride 50% above, 50% below, which means 50% cis, 50% trans. Okay. So in this case, the final product is going to have the hydrogen and the chlorine, 50% cis, 50% trans. Why? Simply because it goes through a carbocation intermediate. It doesn't matter what kind of carbocation. The fact that it goes through a carbocation intermediate means that it's going to add 50-50. Now, where have we seen this before? The racemic mixture that I get from what kind of reaction? SN1. So remember, the second step of this addition is SN1. And so if you form a carbocation, you're going to get the chloride adding to make a racemic mixture. In the new context of adding H and Cl, it just means it's going to be 50-50. Okay. So it's just going to be a 50-50 reaction. Okay. So how does it add? 50-50. And we're going to have a general rule that says any of these mechanisms that go through a carbocation intermediate are always going to be 50-50. So it's going to be a few reactions before we get to something that's not going to be 50-50. It's also going to be a few mechanisms before we get to something that's not going to be Markovnikov. So as we start these reactions out, H plus H2O, HCl, what am I adding? HOH, HCl. How? Markovnikov. How? 50-50 cis and trans. Okay. So as we go through the reagents, you're going to want to make a table, or I will make a table. I think I've already made that table. And so that's what it's going to say, is 50-50 for each one of these. Why? Because it undergoes a carbocation. Any reaction in the future that undergoes a carbocation intermediate will also be 50-50. And maybe Markovnikov. And the reason I say maybe is because you have to add the H plus. Okay. Everybody okay so far? Okay, what would be the major product of that reaction? And you can discuss while you're doing this. We should probably start working in groups the entire time. Random groups. And when you have your answer written out, hold it up. Close.
Is it with or without a microscope?
Without rearrangement. So without rearrangement, take a look at that again. Okay. Take a look at it again. Okay.
Yeah, it's just
Okay. Look at it again. Okay. Yeah. Close. Which one is it? The top or the bottom?
The bottom.
Yes. 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 Now, if you have the first one, that was without rearrangement, can you write the product with rearrangement? If I said, let's write the product with rearrangement. Close. Okay. Bottom one?
Yeah.
Yes. Yes. Although I'm going to have an editorial comment on those. Close. Okay. For rearrangement? Yes. You're close. Okay, now rearrange it. Okay. Yes.
Does it have to be a methyl shift or maybe a hydride?
It's going to be whatever shift obeys our rules. Remember, our rules are one shift to a more stable carbocation. Yes. 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 Yeah. Yep. Okay. What nucleophile are we adding? That's the rearranged one? Yeah. Yes. Although I have an editorial comment on those. Yes. Okay. Was that the answer for the entire group, by the way? Okay. All right, so all I did here was change my water to an alcohol. So remember, HOH reacts exactly the same as ROH. So in terms of writing the mechanism, my choice is I'm going to add H+. Am I going to add it to carbon A or B? Markovnikov's rule would say I need to add it to the H+. I need to add to carbon. Okay, on 3. I'm going to add the H+ to carbon. Thank you. B. Why? Because I'm going to form the more stable carbocation. So if I add my H+ to carbon B, I'm going to end up with a secondary carbocation. And then what is going to add to that carbocation? The entire alcohol. So then the entire alcohol adds. I end up, and this is my editorial comment on this, because this is a pet peeve that can become more than just a pet peeve of mine. It can become actionable, like minus points. What is adding to the carbocation? What atom? Oxygen. So what do you need to show a bond between that carbon and the oxygen? So you need to show this. Okay. You need to show the oxygen with the bond. Not CH3. If it's CH2, CH3, not the carbons, but the oxygen. You need to show that bond to the oxygen. Then that would have a positive charge, and then what's my final step? Lose the H plus and form the final product, which again has the bond to the oxygen of the CH3. And I noticed on the exam, since it was very similar to this, I saw lots of bonds not to oxygen. So you may have seen I wrote them. I'm not going to do that next time. So you want to make sure you always show the bond to whatever atom is there. Okay. Right. So that would be unrearranged. The other part of the textbook, the reading for today, was what happens when it's rearranged. Well, when it's rearranged, we do the same thing that we just did the other day, which is, that's my alpha carbon, that's my beta carbon, that's a beta carbon. So remember, I'm only doing a 1-2 shift. I have a hydrogen here that I could shift. I have a hydrogen here that I could shift. I'm going to shift the thing that makes the more stable carbocation. So in this case, if I shifted this hydrogen over, I'd end up with a primary carbocation. That's never going to happen. On the other hand, if I shifted this one over, do I end up with a more stable carbocation? Yes, I end up with a tertiary. And then what happens after that? Then the entire CH3OH comes in and adds, and we get that rearranged product. So it's possible for HX, H plus H2O. Now I've expanded this to be H plus ROH. It's possible for those to undergo carbocation rearrangements, but the rules are exactly the same as what we talked about earlier this week and last week. Okay. Right. Does that make sense to everybody? Were there any questions about any of the stuff in the chapter 12, in the beginning part of chapter 12? Because if I remember correctly, there was carbocation stability, hyperconjugation, which is why the tertiary is more stable as a carbocation. That's kind of now's not the time to be given. That should have been back in the other chapters, and we kind of talked about that. Then hydrohalogenation, regiochemistry, Markovnikov rule, stereochemistry, which is it's always going to add 50-50 because it's a carbocation. And then it said hydrohalogenation, carbocation rearrangements, and then hydration, acid catalyzed, which is H plus H2O. And then for next time, it's going to be hydroboration, oxidation, and a bunch of mercuration, and then probably bromination will be for Friday. And those will have a different mechanism, and we'll need to talk about a couple of aspects of that. But is this okay? Any questions about that? Okay. We have 5 minutes left. Never misuse 5 minutes. So since you have the dreaded chalkboards, let's go back and look at these cyclohexane alkyl halides. And remember that for this reaction, I could say, let's give me the major product when there's E1. Give me the major product if I use NH2 minus as my base, which automatically means that it will go E2. And for 3, what would be the major product if I used tertiary butoxide in an E2 reaction? Okay. So let's just, for the moment, deal with E1. So what would be the major product or products, plural, of that? Okay, is there another one? Okay. I think you're missing the groups on the ones. Yeah. Okay, is there another one? All the major products or product. Well, here's what I think we need. Here's what I think we need to do. I think we need to make this a graded problem for Friday. Okay, so for each one of these conditions, tell me what the major product or products would be. Okay. So remember the rules. There's no stereochemical relationship necessary for the beta hydrogens for E1. For E2, the hydrogens must be, and they must be trans to the leaving group. If they're in the ring, if they're outside the ring, you'll have to think about, can I deprotonate those? And then what's the major product, whether it was NH2 or tertiary butoxide. Okay. So we'll make those due Friday. Go ahead and put, when you put your things back in the, put the boards back in the, just give them a quick wipe. Put the boards back in the basket, the paper, or the, these things back there, and then I'll take the markers, because that's going to be a nightmare trying to fit them back in. I think.
So do we not have to show the transition states or anything for the problem?
No, just the final product. No mechanism, no transition state, or anything like that.